Roberto, who's instead gonna talk about ClassyQ. So we go now from big centers to a library, I think.
Yes.
For polarizable models. Yes, 20
Okay.
minutes, floor is yours.
Yeah, thanks. So different, maybe. So I'm part of one of these competence centers that Diana was speaking about, and also Daniel is introduced. So I'm part of one of those ENCCS. So Diana was saying you can look at our website, the ENCCS.sc, and look at what we're doing. We organize training events. I have one next week. We're going to teach MPI programming. So if you want to register for that, I think it's still open. If you're interested. So what I'm going to talk about today is this new library for, in general, quantum classical polarizable models. You can call it classic or ClassyQ because it deals with point charges. In principle, coupled with quantum description of the solid. And that's the one there. No? Yeah? Maybe. Just use this. So I work as a research software engineer. My background is in quantum chemistry. So I spent a lot of time during my PhD and my postdoc and now in my job thinking about design, software design, and software engineering best practices. And this talk is about designing this new library, but also thinking about what is good API design. So an API is an application programmer's interface. If you're used to working with web services, all these web services talk together with well-defined interfaces, they're well documented. And what I try to do in my job is think what is a good way to kind of exploit this model when we talk about scientific software development. And I think we can define three main categories of API design. So we have what I call by consensus. And you can think about Blas and Lapac in that case, because there's been people that work on linear algebra backends for many years, and they came up with this model, which is standard of defining how do you do matrix multiplication, that's GEM, how do you do Cholesky decomposition, how do you do Gaussian back substitution, and so on. And these are standardized by adoption. So winner takes all. Everyone uses Blas and Lapac with the given interface, and that's the interface by which you define Blas and Lapac. And that's one way of getting an API. It takes time, but it can work. Then you have another example, which is called by committee, and you can think about MPI or OpenMP. There's a committee that forms, they sit down and they say, how do we do message passing for parallelization? How do we do shared memory parallelism? They define a standard, there's a document, I think the MPI standard, now it's like 400 pages, you can read it. And then as an implementer, you read the standard and implement the functions as they are defined by the standard, by the community. So this is standard by construction, meaning that the committee decided what the standard should look like, what the function should look like, and that's how you will use it. And then the last example, which I think is what most relevant in my case, when working on continuum solvation and solvation models, is what I call bi-feedback. So it's not really a standard because there's someone like me who sat down and said, I want to solve this problem with this software, let's say OpenMolcas or Dalton, and I want to implement this as a library. I want it decoupled from the specific quantum chemistry program so that I can reuse it in different codes. But that's just me sitting down at my computer and writing the code and then interfacing with the different quantum chemistry packages. So this is not a standard, as I said, but it could become standard. And there are examples where things become standard. So I list two here. So this XC library, which some of you know. Most people nowadays use libxc to get exchange correlation functions. So we can say that libxc has become the standard by feedback from the community, if you wish. So that's why I need the Google slides, because I had some animations. So this is a bit how API evolves, but what makes a good API is if it, in my opinion, if it respects three properties. One, it is extensible. So within the library that you're developing, let's think about MPI or Blas and Lapac again, you can still add new functionality with low friction, meaning that me as a developer of my own library, let's assume I'm developing Blas, I can add a new function that does some new form of decomposition, and I can do it without spending infinite effort in adding this functionality. So Extensible is a library that can grow with low friction. And a library should also be modular. The API is modular. I can build new functionality on top of it using functions that sit below. So this is, I call it the Lego principle, because the Lego offers a really simple interface by which you can build up a house. In this case, it's not in a house, it's something else, but you get the gist of it. So do one thing and do it well. This was also what Anthony suggested about T-Rex.io. And then it needs to be sustainable, meaning that I want to use software, so I don't want to do anything weird, because this makes my life easier, makes the life of other people easier. Imagine if we didn't have BLAS and LAPACK as a standard. Imagine if everyone starting a new quantum chemistry code had to write those functions by hand. They wouldn't be performant, most likely. And every time you need to learn how to use code into a new quantum chemistry program package, you would have to learn how to use these primitives. So we're very lucky that there are primitives in libraries already. It makes our life easier. So let's bring this general discussion into the heart of the topic. So quantum classical polarizable models. What are these? Okay, you're well aware that if I have a molecule in a solvent, I could model everything with quantum mechanics. I would probably use DFT because the system is very big and I don't have the lifetime of the universe to wait to get my energy. Of course, this is really expensive still, even if it's DFT. And it's probably very useless because you need to do sampling. Like you need to sample different configurations of the solvent to get an answer that makes sense. So in the many years since the Schrödinger equation has been there after DFT, there have been approaches that have simplified the way you treat this problem, because mostly we're interested in the property of the little molecule that sits in our solution. In this case, it's one. So one of the approaches is to say, let's just forget about the water molecules and I just put the continuum outside. And then I have just my little molecule, which I treat the QM level, and the rest is the classical problem. I have the continuum, which is polarizable, it's parameterized with a given permittivity, and I just look at the coupling between them. And that can be done rather easily. If I want to be a little bit more sophisticated, then I say, instead of removing water molecules, I keep them, but I don't do a QM calculation on them. I just put some classical parameters. It can be point charges, can be point dipoles, or point multiples in general, polarizabilities. If you want it polarizable and not just a precise embedding, you name it. There are many models that do that. Next level of sophistication would be to combine the two, so that you have a QM layer and a MEM layer and then a continuum layer. That's a technical problem. The principle remains the same. So what I would like my library to do is essentially to treat these two cases, and this case as a kind of simple generalization. All in all, if the library works as I would like it, if it respects the three principles that I outlined before, a QM code will not see much of the details of what kind of models I'm treating. It will just see a Fock matrix contribution or an additional energy contribution, and all the details of how do I define the continuum, how do I define the MM layer are hidden behind the library. Then I can keep caring about what I care about, so the classical models, and the QM implementer can just care about how do I make the QM calculation fast. So let's look first at the continuum model, because I come from a continuum model background. That's what I did during my master and PhD. So the problem is a completely classical problem once you define the density of the molecules inside. So this density can be classical or quantum mechanical. It can be DFT, ClassyCF, couple cluster. I don't care. It's density. And the problem outside that I have is this continuum, this block around, and the boundary between my molecule and the block around is what I call the cavity. So this thing called omega I in the picture with a boundary, closed boundary called gamma. So this is called the transmission problem in classical vector statics. I have a linear elliptic differential operator inside that describes how the environment responds to the fact that there's a charge inside. Similar elliptic operator outside. and jump conditions for the function itself that I'm seeking and for its derivative, and then some radiation conditions so that the solution doesn't blow up. So this is standard. If you take any text in physics, you will see this development. I'm not saying anything new here. What we do in continuum solvation is to say, I don't want to solve the differential equation because that's defined in 3D space. I would need to put a grid in space and then discretize the problem there. It's feasible, so I find an element method, but it's not the smartest way because I know that I have a closed boundary. So what I can do is by linearity split this function that I'm seeking into the electrostatic potential that I have in the cavity if there was no continuum around, plus correction, what is called the reaction potential. And this reaction potential, by virtue of the fact that I have a boundary between two regions, is expressible as the integral of a surface charge. So from a 3D problem, I kind of project it down in some way to a surface problem. So easier to solve, and it's easier to solve because this differential equation turns out it's equivalent to an integral equation defined on the boundary. And this sigma that I put there in the reaction potential is unique solution to this equation. So, okay, that's the kind of theory framework. This is still my molecule in the environment, in the continuum. So we have a classical continuum polarization that affects the charge density, which is a quantum charge density inside the cavity, and vice versa. So the two problems are coupled, because of course, if I change the charge distribution inside, the polarization will change, and so on. So they need to be solved for self-consistently, and this can be done within the self-consistent cycle in the computational program. But the ingredients from the classical point of view, which is what I want to implement in my library, is to have a definition of the molecular surface, so the boundary between the inside and the outside region, and a way to create a finite element partition for it. Because the boundary can be extremely complicated, and it will not have an analytical form, most likely, and if it has, I don't have a way to represent the integral operators analytically on this arbitrary boundary. Then once I have the boundary, these integral operators will have to be discretized on it. This is called boundary element method. Again, it's rather standard in the mathematics literature. And this gives me a matrix problem, a linear equation, and then I need a linear equation solver. So these are the three things that I need on my side, essentially. So how do I build this library? And most of all, how do I grow an API that respects the three principles that I outlined at the beginning for quantum classical polarizable methods? And now I'm including not only the continuum, but also molecular mechanics methods, and they can be polarizable or non-polarizable, because that in the grander scheme of things is a technicality if they're polarizable or not. So let's start with the requirements. What I want is to have interfaces to see Fortran and Python, and this is the same that Anthony mentioned yesterday for TRX-IO. That's for maximum chance of interoperability with all the. Then I want an open source license. Again, maximum interoperability and reusability. And it should be numerically robust. And I will show what the problems are with continuum models. It should support continuum models and molecular mechanics models on the same footing. And it should give access to molecular geometric derivatives. This is something that is important for many codes because you want to do geometry optimizations. So it turns out that I did write one such library back in the days of my PhD. It's called PCMSolver. You might have heard of it. You might not have heard of it. I don't know. So this was mostly research project. So I was doing this because I needed to get my PhD. But I did focus on software using sustainability. And the outcome was that this library nowadays is still used. It works. And the last time I counted, there's like 13 codes out there that are open source and available that use this library to provide continuum solvation. So it was kind of a success, I guess. However, as I here, I was very young, well, not that old now, but I was naive, meaning that this was a research project. So there were some numerical stability issues, but it was in some corner cases that were not relevant to my research. So I kind of swept them under the carpet and thought, okay, maybe they just happened for this case and I don't care. Let's move on. I cannot compute molecular gradients. so I cannot do geometry optimization with it. And again, that was not relevant for my research at the time, so I never cared about implementing monetary gradients. It's a big mix of C++, Fortran, C, and Python, and not in a layered fashion in interfaces. So they come, like some pieces are written in Fortran because we use some old code that supervisor is written, and then I wrote a C interface on top of them to make them talk with the C++ part, which was mostly what I had written. We have some input parsing in Python. So not layered model. And most of all, it violates the first principle. It does work, but it's not extensible. I cannot improve it anymore, any further that I've done without doing a full rewrite. And we were talking about this at lunch with Giovanni yesterday, that it's not always economical, like in terms of your time, to do a full rewrite. But this got to the point where it's absolutely impossible for me to add anything that might fix these three problems. So I went on and said, okay, we got in touch with Roland, and I said, okay, I see that your continuous solvation library is pretty old. I'll rewrite it for you outside of Molcas. So I started on this project. It was January. And the first thing that I needed to do was, okay, let's define the cavity. And this again is pretty standard. I put a sphere with certain radius around each atom, and then I compute the union of these set of poles. So this is easy, okay? So interlocking spheres, I can use van der Waals radii, scale or unscaled, and also get what is called the solvent accessible, which is the one that represents the I cannot give what is called the solvent excluding surface because that's defined in terms of spheres and tori, and that's more complicated for me. It doesn't have a closed analytical, so that's more complicated for me than to move on and do the finite element partition. So the scheme that I want to use uses points and weights. So if you're familiar with how DFT is done, it's basically bucket partitioning applied just to the surface and not to the volume. So on the unit sphere, I create a simple partition. It's called the Leopardi partition by the guy that first defined it. So it basically guarantees that on each sphere, I get a certain number of points and all at the same weight, and they sum to the total surface of the sphere, and they have some guarantees on the integration. And then the molecular surface is built as a product of the unit partition in each sphere with some smoothing factor for the fact that when the spheres intersect, I don't want just to jump from the points of one to the points of the other, but I want to smoothly transition from one to the other. And this is what makes it possible to implement molecular gradients in a robust fashion, because then I don't have jumps in the potential energy surface if I use this form of the weight here. Once I have the partition of the surface, the next thing that I implemented was we have these integral operators. What is their matrix form when I have the surface discretization? So everything is rather easy. These are Coulomb and electric field operators on the surface. So when I have 2 points that are disjoint, the formulas are easy. You can just use the formulas for the potential and the electric field at that point. Of course, if the point is the same, so if I'm looking at self-interaction, these formulas will explode because this is 1 over r and this is 1 over r squared. So I need to do some form of parameterization. And I use a formula that Salmani and Fish proposed for the implementation in Gaussian. And using these factors, Fi and Gi, even though they're parameterized using some discretization formula on a single sphere, they give results that are actually quite robust, meaning that even if I have a complicated topology, I don't get ill-defined matrix elements. It does preserve the properties of the parent operator, so positive definiteness, and negative definiteness, and it gives me monotonic convergence of the integrated charge, meaning that if I have a finer tessellation or discretization, I still get convergence to the exact result. So the last ingredient is the linear equation solver. At the moment, I'm just using a CAN solver, meaning I have a library, so Blas and Lapat again, to do either Piotr Cholesky for a symmetric positive definite operator, like the conductor-like model, or LU, the composition. This is not very smart though, because this is n cube for the computation, and I have to store the matrix sum, so it's n squared. So this is pretty much still a work in progress. So there is no interface with OpenMolcas yet. I thought there would be by this meeting, but there's not. So I'm not very successful in my work. What do I want to do before I write the interface and replace the current module? So abelian symmetry should be there, because it's important, especially if you want to do high-level correlated calculations. The geometric gradients are still not there yet, even though I have derived the formulas and they should be rather easy to implement. And if I have a number of finite elements is above 1500, doing Cholesky or Edu, it's not going to cut it. So what I need to implement is this matrix-free iterative algorithm with convergent acceleration, so Jacobi iteration with the APRS. And that basically brings down the storage requirements to linear in the number of finite elements, and the computation requirement to adapt in the number of finite elements. And then for the future, I could think about fast multiple method, because these are Coulombic operators that I need to implement, and then the computation requirement might go down to linear in M as well. And then the last point, which was one of the points that basically was the biggest complaint about my former library, PCMSolver, is this API for input processing, so that you can pass information between the two codes without having to do a pre-processing with some random Python script that I wrote like 5 years ago. So this is still ongoing, and I don't have a good API for it. Thank you. So this was all about application programmers interfaces, not many results. But I hope you enjoyed it, and that probably gives some food for thought for the discussion in the afternoon. I don't know. Well, thanks for your attention.
Oh, thanks, Roberto. Do we have quick question in the audience? I have a very quick one.
Yes.
How is it gonna be for electronic excitations? Do you plan on fast to slow response, or?
Yeah, so I've implemented that for linear response in Dalton, and there it's very easy, but if you have state specific methods, it's not as easy. It's not just switching one dielectric primitive. You need to keep in memory a couple more vectors of polarization.
It's gonna be there, or?
Well, it has to be there, because if it needs to replace the current library in OpenMolcas, I cannot just give some half-baked stuff. So,
good.
I mean, that was
good.
yeah.
All right. Okay.
Okay, thanks.
So yes, let's thank Roberto again.